Continuing education knows that at the end, students want to graduate, and we can help them do that because we take the time to really listen to their needs and we understand all the different options that are available across the campus for them.
We don't take a cookie cutter approach. We realize each student comes with their own story. So whether it's a part-time student looking to complete a degree program or someone just looking for online courses, we're there to connect them to the resources of the university.
Thank you for joining us. It's Friday, April 14th, and it's 10:30 a.m. In case you need to do check your watch or your date on your watch. Good morning, and thank you for joining our session on carbon capture, natural and technological solutions. We have a very engaging panel of experts here in front of you that you'll learn a great deal from. And the session will run until 11:40 a.m., and we'll have time for your questions and discussions after some short panel presentations. I'm Dr. Bill Doe with the College of Engineering and Applied Science here at the University of Colorado Boulder. I work in the Dean's Office, where I manage strategic research initiatives for our college faculty with federal agencies, industries, and foundations. I'm a civil and professional engineer with expertise in water resources management. And prior to my university career, both at Colorado State and CU, I was an engineer with the U.S. Army Corps of Engineers for 25 years. Let me talk before we get started with reading the CU Boulder land acknowledgement. Today, we'd like to acknowledge that Boulder is on the ancestral homelands and unceded territory of indigenous peoples who have traversed, lived in, and stewarded lands in the Boulder Valley since time immemorial. Those indigenous nations include the Apache, Arapaho, Cheyenne, Comanche, Pawnee, Shoshone, Sioux, and Ute. Thank you. As I mentioned, we're going to reserve time at the end for discussion of Q&A. We're using a note card system. If you'd like to pose a question, raise your hand and one of our assistants will come by and collect that up from you and let you write your note on there and then give it back to them. And then they'll bring them up to me, and I'll sort through them while we're working through the panel and try to include as many of these questions as we can at the end of our session. Let me start by introducing our panel in the order they will present. To my left, your right, each panel member is going to have about 5 to 7 minutes to provide an overview of their research related to carbon capture. The first two presenters are former colleagues of mine at Colorado State, so this is a serendipitous reunion of sorts. Dr. Rich Conant is a professor of soil biogeochemistry and department head of ecosystem science and sustainability in the Warner College of Natural Resources at Colorado State University. His research specialties include ecology, ecosystem modeling, data synthesis, environmental sustainability, and food production systems. Rich believes that the objective of his work is to foster development of more productive and more sustainable food production. And then the next person on the panel is Dr. Eugene Kelly. Gene's a professor of pedology, deputy director of the Colorado Agricultural Experiment Station, and associate dean of extension at Colorado State University. He's been there for almost 34 years. Gene's scientific specialization is in pedology and geochemistry, with primary interest in regional soil water dynamics, soil degradation, and global biogeochemical cycles. And his current research is centered on soil degradation and regenerative agriculture. Next is Eric Ping. Eric joined Global Thermostat, a company, in early 2013 to lead its technology development team, and is now the vice president of process and operations at Global Thermostat headquarters in Commerce City, Colorado. He's been active in the renewable energy and green technology space since 2005. When he began research working on hydrogen reformation with intelligent energy. And he also spent time here on our faculty at CU Boulder. Finally, Dr. Wilson Smith is a professor of chemical and biological engineering here at CU Boulder, where he holds positions as a fellow of the Renewable and Sustainable Energy Institute at CU and is a senior scientist at the Department of Energy National Renewable Energy Lab in Golden, Colorado. And he was recently a co-recipient at CU of a DU Energy Frontier Research Center Award for research into clean energy technologies and low carbon manufacturing. I'm going to read a very brief statement to get the panel started. I assume you all are well informed on climate change and carbon capture, but just in case, the emittance of carbon dioxide and other greenhouse gases such as methane into the Earth's atmosphere has long been a natural process, which through the so-called greenhouse effect has kept our planet habitable for both species and humans. However, as industrialization, deforestation, and the burning of fossil fuels have dramatically increased by humans over the past century or more, the release of carbon dioxide and greenhouse gases into the atmosphere has radically altered the greenhouse effect and the Earth's global temperature, resulting in the catastrophic effects of climate change that we are seeing worldwide. While changes in human behavior, government policies, and industrial practices are essential to reversing and mitigating the deleterious increases in carbon dioxide, the avoidance and reduction of carbon emissions through carbon capture science and technologies is a critical component of the overall strategy. Each of our panel members will discuss the scientific discoveries and technology innovations that underpin these approaches. And we'll get started with Rich.
Thanks, Bill. It's a pleasure to be here today. I was a student at University of Colorado, so sitting in the audience a mere 30-some years ago, I guess about the time Gene was starting at CSU.
That's really funny.
And I remember the Conference on World Affairs was one of the things that I really appreciated about CU. It opened my eyes to kind of the possibilities. So pleasure to return in this way. Let me first say that a lot of what we hear about climate change is scary. But I think there's a lot of reasons to be optimistic too. This past year, Congress passed the Inflation Reduction Act, which is enormous in many ways and is going to drastically change our trajectory when it comes to emissions. And we're going to see emission reductions that we thought weren't possible. One of the things I do at CSU is I teach a class called Foundations for Greenhouse Gas Management and Accounting. And it's a fun class. I really enjoy doing it. And since I've been teaching it, the first time in 2013, there were 3 or 4 students, and about that many per year until just a couple years ago. And I had 40 students, last year 50 students, and this year it's going to be like 70 students. And so the changes that we're seeing in policy are being reflected in the changes in enrollment and changes in action. So lots of reasons to be optimistic. One of which is that students are concerned about this and they're educating themselves to do something about it. My work, as Bill said, I'm a soil biogeochemist, so I knew a little bit about biology, a little bit about geology, and a little bit about chemistry. And I try to apply that knowledge to understand carbon, nitrogen, phosphorus cycling in soil. And a lot of my work has been to try to understand how come some carbon that's introduced to the soil sticks around as organic matter for thousands of years, while much of it decomposes in minutes, hours, or weeks. And like the policy evolution that we've seen, the change in the field of soil science when it comes to understanding of carbon cycling has been really dramatic. It's been a fun place to be. It's maybe a silent revolution, but it's one that I feel lucky to have been part of. So we've learned a lot in the last couple decades about why carbon is stabilized in the soil. And the research that my lab group does is focused on trying to apply that hard-won knowledge about what acts to preserve carbon in the soil, so that we can augment those processes through kind of bioengineering. So for example, we're working on a few projects where we're trying to coax plants into making compounds that are sometimes called biologically adjacent. So these are compounds that plants may be capable of synthesizing, but that don't seem to decompose. And if we can engineer plants to make a little bit of carbon that is resistant to decomposition, then we have a vehicle to sequester massive amounts of carbon in the soil. And so I'm working on that, trying to understand the dynamics, working with plant scientists to try to engineer these processes into plants. And it's really exciting. And it may, one of the things I like about my job is that I can change direction, take risks. And this is really risky, and it's been a lot of fun. We've learned a lot about things that people haven't really thought much about, and it's been super exciting. And the upside is that if this works, it could be a vehicle to draw down massive amounts of carbon. As Bill said, we have this problem of CO2 in the atmosphere, And even given the policies that have, or the agreements that countries have entered into today, it's still going to be hard for us to maintain 2 degrees C change or less. And the IPCC states that the Intergovernmental Panel on Climate Change says that we need to remove something like 10 billion tons of CO2 from the atmosphere every year, starting fairly soon. And that's what we're talking about today. That's going to be hard to do. 10 billion tons is a lot. It's about the equivalent of the emissions from the world's automobiles. And so reverse engineering systems to take that much CO2 out of the atmosphere is a real challenge. From my perspective, plants are very good at taking CO2 out of the atmosphere. And if we can just change a trickle of that flow of carbon that plants fix into decomposition-resistant compounds, it could be world changing. So there's a huge upside to the research that we're doing. And I'll be happy to answer questions in more detail as the panel progresses.
Thank you, Rich. That's a great summary. Gene, you're on.
Yeah, okay. Well, thanks. Rich provided first of all, it's a pleasure to be here. I'm not from CU, but they got all my money because my kids went here. So anyway, I'm a professor of pedology. If you don't know what I study the origin and evolution of soils. So I've worked, a lot of my career has been developing theoretical aspects of studying soils and how do you define a soil and how do you measure it. Over the last 10 to 15 years, I've been drawn to the issue of soil degradation, and 65% of the planet's soils are in degraded form. So we have a big problem, right? And in my current position, not only as a professor of pedology, but I have to oversee the agricultural research that occurs at CSU and around the state of Colorado, and there's a lot of opportunity. When we look at global greenhouse gas emissions, about 34% of the greenhouse gas emissions are from the food sector. You slice that a bit thinly, about 28% of that comes from agricultural activities, right? So we have not only the agricultural activities, but we have the food production end of things that are greenhouse gas emitters. There's an enormous amount of pressure now on the scientific community to come up with ways of making agriculture carbon neutral. I mean, that's what has to happen at some point. Before you start sequestering it, it has to be neutral, right? So that's one of the aspects of it we work on. One of the things you'll hear a lot about, it might come up later in the panel, is the idea of regenerative ag. You know, what does that mean, right? Well, we don't really know yet, right? But we know what regeneration means. And I think from the standpoint of agriculture and building healthy soils, we kind of know what has to be done. And we know where the science is. And I think the opportunity for us is to really make sure that we don't reach beyond the science. And that's kind of what I spend a lot of my time doing. So I'm at a lot of these things, and soils are probably the best. You know, actually, soils are more popular now than anything. I can't believe that people really know what soil scientists do, actually, because it's in movies, it's on TV, people talk about it all the time. But it's this enormous resource, the skin of the earth, that we just need to know a lot more about it, right? Before we start, monetizing things and relying on it for certain aspects of it. So anyway, so my basic ploy today is to really talk more about some of the aspects of regenerative processes in soils globally, and also we have issues and challenges right here in Colorado with that as well. So anyway, I think I'll leave it at that. Anyway, yeah.
Good, thanks. That's excellent. Thanks, Gene. We're going to kind of transition from talking about more the natural processes in soils and plants to more kind of the technology slice on this. So Eric will go first on that.
Yeah, great. So thanks, guys. And yeah, as Bill mentioned, Rich and Gene have spent the majority of their career looking at sort of the agricultural and the natural methods for carbon mitigation. I think we'll be talking more about the sort of more industrialized and chemical methods of carbon mitigation. So Global Thermostat, the company that I work for, our focus is direct air capture. So for those who aren't familiar with it, it's directly processing the air and extracting the carbon dioxide that's already been emitted over centuries of industrialization from that air, and either using it directly or sticking it back underground where it came from. So it's really important to get out there in the front and mention that direct air capture, and you'll hear me refer to it as DAC, D-A-C. It's not a substitute for or an excuse to delay renewable energy expansion and adoption, increases in energy efficiency, and other energy decarbonization efforts. And it's also not an alternative to things like soil remediation, afforestation, things like post-combustion capture, enhanced weathering, or transportation electrification. Rather, it's a supplement to those things, and it's a supplement that's both scalable and economical. It allows us to recapture hard-to-abate emissions. It allows us to attempt to drop down some of the historical emissions that have sort of gone unabated for the better part of a century and a half. And it's basically leaning on 50, 60, 90 years worth of chemical, mechanical, electrical engineering knowledge in the industrial space to kind of apply those levers for trying to reverse some of the CO2 emissions that have historically been released. So our methodology for doing direct air capture is basically like a large filter that you process a whole bunch of air through. So you got to process an enormous amount of air to get even a small amount of CO2, just given the very low concentration of CO2 in the air. Right now it's somewhere in the 410 to 440 parts per million range, so 0.04%. And the product from direct air capture is a high purity CO2 stream. So it's something that can be directly stuck back underground, or it can be utilized. So direct air capture does about a 2,500x concentration of atmospheric air, producing this CO2 stream. There's a current market, and CO2 is a widely used industrial component, right? So it's a feedstock. There's like a $7 billion global market right now for carbon dioxide for people who are using it. And you hear a lot of commentary in the climate space of how big of a liability CO2 is, but it's got a lot of intrinsic value for those that use it. Things like beverage carbonation, greenhouse agriculture, feedstock for plastics and building materials, et cetera. Obviously putting aside any sort of use for increases in oil recovery methodologies that are being used right now in parts of the U.S. But it's a highly valuable molecule, and there's major supply chain issues for it right now. So CO2 is an industrial byproduct generally from ammonia production, from ethanol production, and when those plants shut down, the place they get CO2 from is underground. It's actually reverse sequestration. In the US, a huge amount of the CO2 that's used industrially is pulled out of stable geologic formations and then used and re-emitted into the atmosphere directly as CO2. And earlier this year, for example, the largest geologic formation that's sourced for CO2 in the US in the Jackson Dome was poisoned, and they weren't able to use it, and those that needed CO2 couldn't get it. So on one hand, we have this problem where there's way too much CO2 in the air globally. And on the other hand, there's people who need CO2 and can't get it. And one of the things that direct air capture can accomplish is basically there's air everywhere, and so you can have a little bit more supply chain security if you can create your own CO2 at the point of use where you need it. It's one of the crutches that allows kind of the scale up of direct air capture approaches to get to climate relevance, which as both the moderator and the earlier panelists mentioned is on the scale of gigatons per year. You can't go from nothing to billions of tons per year in capacity, but rather take steps up in capacity, thousands of tons, hundreds of thousands of tons, millions of tons. And being able to sell CO2 into the merchant market that offsets what would be otherwise stable CO2 pulled up and re-emitted allows us to both sort of ride the learning curve for evaluating and deploying new emerging technologies while still making an impact on overall sort of abated emissions as we approach climate relevance at sort of the billion of ton per year scale. So happy to talk much more about this as the panel goes on, but at this stage I'll pass it over to Wilson.
Thanks, Eric.
Thanks, Eric.
Well, thank you all for being here. I'm going to kind of take over where Eric left off. So what they do is take the CO2 out of the air, and then they concentrate it and get pure CO2. You can either take the CO2, stick it underground, which is what we need to do with most of the CO2, but we can also use the CO2 in a lot of ways to make things that we need, like chemicals, fuels, pharmaceuticals, and plastics. Currently, how CO2 is utilized to make a lot of those things, even the chairs you're sitting in, the polyvinyl that's sitting there, is using CO2 plus hydrogen and using very high temperatures to convert things like plastics. The problem there is that the very high temperatures required can only be achieved by burning fossil fuels to get that amount of heat. So what we try to do specifically at the National Renewable Energy Lab is to look at CO2 conversion methods that use renewable electricity, so electricity made from PV or wind or nuclear or anything that's non-CO2 emitting, and do electrochemical conversions of CO2 into the same kinds of products. So in that way we don't do what a lot of people call decarbonization. and it can be a very misleading word. It makes it seem like we don't want carbon. Carbon is fine, but what people mean when they say decarbonization is that when we make a lot of chemicals and fuels and a lot of power, we emit a lot of CO2. So decarbonization is a synonym for saying we don't want to emit CO2. Instead of making the same chemicals and fuels that we all need and use for society, what we want to do is a defossilization of them. So instead of using the carbon that we get from fossil fuels to make the physical materials we have, we want to use the carbon in air that people like Eric and other companies can capture. And so there's a lot of different approaches to this. Again, the major one we can do to get away from high temperature processes that emit CO2, we use things like electrochemistry. So you may remember in high school or junior high school, if you just take two pieces of metal, give it a few volts in water, you see things start to bubble off. That's a water splitting reaction where you take water and you make hydrogen and oxygen. It's the same exact technology, except you put in CO2 or some form of CO2 that's very good to be converted, and we can make things like synthesis gas or ethylene, precursors that are used in the chemical industry that can significantly remediate the amount of CO2 that we emit. The other approach that people are using for the CO2 conversion is, as Eric mentioned, there's this step where you capture the CO2 and it binds to some material called a sorbent, and then it takes some amount of energy to release the CO2. And the amount of energy to release CO2, depending on how you absorb it, can be prohibitively expensive, meaning it will cost too much money and too much energy. So there's an emerging type of approach where we can take the CO2 in its already captured form, and instead of regenerating pure CO2, we can directly convert it to make chemicals and fuels. From a chemical engineering perspective, this means instead of using 3 or 4 different reactors, we can use 1 or 2. So it simplifies the process, it makes it a lot more efficient, and it gives us a whole wide range of chemicals we can make. Essentially with water and CO2 and electricity, we can make any form of hydrocarbon, fuel or precursor. There's 20 different products that can be made. So the challenge there is being able to do this very selectively. You want to only make 1 compound at a time instead of 20, and do it very energy efficiently. And finally, one of the most emerging ways that people are finding new ways to use CO2 that doesn't make fuels that would be burnt and re-emitted to the atmosphere. There's a growing movement on CO2 mineralization. And so essentially, if you take CO2 in different forms and you make it very basic, you form carbonates, which are the precursor for use in things like cement and building materials. So the idea there is that we can take the CO2 from the air, instead of turning it into some form that would either degrade or be burnt and emitted back into the atmosphere, we can take the CO2 out of the air and physically make all the buildings and materials that we use around the world. And that's something that's applicable across the world. It's not just something where we have big grids here in the US. That is a translatable technology that can be deployed around the world. So I'll leave it there as an open end of what we do with CO2 and kick it back to Bill.
Well, thanks all. I think we've, but my thought hearing all of you is basically a basic thought that carbon dioxide and carbon by themselves are not evil. I mean, it's just about basically how much there is, where it is, and how we use it. And so I think that's an important lesson that came out of it. We have a number of questions from the audience, and please keep those coming, and I'll try to merge these as we go along. Let me come back to the front end here, which is the natural processes and the soil issues. One of the audience members says, and glad to hear that you're talking about this in the agricultural realm, because we have 9 billion people on the planet that have to be fed, right? And so the question, I think, is really about the scale of this. In other words, how do we take some of the work you all are doing in the soil binding and some of the bioengineering to get to the scale of 9 billion people needing food production on the planet?
Okay. Go ahead.
Well, I mean, that's our challenge, right? In other words, the idea of sort of regaining the soil health of the planet and feeding 9.5 billion people. So, you know, we have to be cognizant that you'll frequently hear, you'll see in the literature, and Rich would probably chime in on this, that, you know, there's been a lot of interest in the idea of sequestering carbon in soils somehow and making that sort of the major metric we use. And what some people worry about is that we don't want people just focusing on that because we still have to feed the planet, right? So soils have like a dual function. They'll call it a win-win. They say, well, we're fixing carbon and we're producing food, right? And so there really are, they're kind of related, but not really. So we don't really know for sure what are the effective practices for doing both. right? And so that's kind of one of the challenges. But there's nothing, I would never argue that fixing carbon in soils is a bad thing. It's a really good thing. It's the best indicator of ecosystem status on the planet. If there was a single indicator, that would be the one I would pick. But in terms of getting to the point where we can actually monetize that and make it profitable in an agricultural realm, I think that's going to be really challenging, because of not only Rich will talk more about the biophysical limitations in terms of the chemistry and all the science behind it, but then you have your sociological challenges as well, right? And we know that those are not only in the United States but globally. And then finally, the economics of it, right? How does that all come together? So anyway, I don't know, Rich, if you want to.
Sure, yeah. So maybe two thoughts. One is that there is clearly a risk that carbon could be stored in soils, and that the trade-off would be reducing food production. It's conceivable that we could reforest land and not use it for food production. But we have a planet of 8 billion people. There may be 10 billion people by 2050. Thankfully, people are growing wealthier, eating sufficient calories, and I think with wealth will come people eating higher up the food chain, so more calories. And so, efficiently using our agricultural land to produce food is quintessential. The work that I've been involved with that's assessed the potential for carbon storage has typically tried to imagine a world in which we don't compromise and don't reduce food production, but in fact increase food production to meet the growing demands, and then estimate how much carbon might be stored on top of that. There are many practices that can rebuild soil carbon stocks without sacrificing food production. And those are the things that we tend to focus on. However, as Gene alluded to, if there is a market for storage of carbon in soil, then it's conceivable that that market drives out low production agriculture, which is what most of the world depends upon for food and for income. We did an analysis looking at intensification of livestock production systems, and we calculated something that we called the marginal abatement calorie curve. How much would people, the poorest people, have to give up in terms of calories that they were able to consume if a carbon market developed? We were trying to demonstrate this trade-off. And so it's really important that like we don't argue that we should draw carbon out of the atmosphere as a way to avoid reducing emissions. We shouldn't draw carbon out of the atmosphere and pay a penalty in food production.
Right.
The work that we're doing uses the same framing. We're trying not to reduce food production, and so we're trying to come up with some creative ideas by which we could deploy plants that might fix carbon and make it resistant to decomposition. For example, using cover crops that are grown not for food production, but to maintain soil health, prevent soil erosion, sometimes fix nitrogen. If we could engineer those plants to do something else, that is create biologically decomposition-resistant carbon, it wouldn't interfere with food production, yet we'd realize a carbon benefit. And so we take that really seriously in all the work that we do. That risk exists, and we should acknowledge it, but work around it.
Yeah, and just to add on to that, this idea of, you'll hear the term frequently intensification of agriculture, that in other words, we need to use the very best land for producing food. And just in terms of the methodologies that we have currently to intensify agriculture, deal with genetics, right? Plant genetics, and also use of fertilizers. And then that becomes another problem because of there's an energy intensive side of fertilizer use, particularly nitrogen. So, the other aspect we have to worry about is as people get wealthier and climb up the food chain, they're eating more meat, right? So that sort of changes the array of crops that we can grow on the planet. And 60% of our corn goes to livestock feed in North America, right? 80% of some in the Midwest goes into ethanol production, right? So it's really a matter of changing the whole thing, as Rich pointed out, understanding the system, but understanding also that it's not only just CO2, it's methane, and then I think nitrous oxide is kind of the real nasty one. Like nitrous oxide, the amount of nitrogen fertilizer that's needed to get to the production levels that we need is a real challenge. And so it's almost like we have to re-engineer our agricultural systems to look at other ways, maybe cover crops, of putting nitrogen back into the system. Because we're really limited by the global stoichiometry. You have carbon, nitrogen, and phosphorus, right? And you're not gonna go outside a certain boundary there. And typically, the Green Revolution was a remarkable thing on the planet. Agriculture was it was highly successful. and the technology, we're paying for that now. I mean, the idea of having to rely on nitrogen fertilizer is a really big issue, which kind of gets overlooked a lot. So anyway, so that's another aspect of it too. It's the whole system of agriculture that you need, not just the carbon. We need to really look at the whole system in terms of what it's doing, not only to the nitrogen cycle, methane production, and in our water. You know, we're focused in Colorado. We focus mostly on water, because water is probably more important than anything in terms of our soil health. It's the largest reservoir of fresh water in Colorado is in our soils, right? So we have to be able to manage those and maintain and be really, 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 really careful with the amount of water we have in our systems. The water limits the amount of carbon we can fix. It's a chlorophyll-limited world, right? Whatever, like chlorophyll's king, right? So Rich is right on with the plant adaptation. I think that's really interesting work they're doing with that. Yeah. Anyway.
One of the audience members asked about photosynthesis. Is there ways to improve or bioengineer photosynthesis to be more efficient and more solving the problem?
Maybe. That's a hard. I mean, there are a lot of people that are working on ways to enhance photosynthesis, and it's you know, it's not that easy. Plants have evolved over a long period of time to optimize a whole range of different trade-offs, and they've arrived at a few different pretty inefficient systems when you think about the energy harvesting efficiency of photosynthesis. But there are lots of groups that are really putting in efforts to try to tweak photosynthesis to make it more efficient. I haven't seen really even in trials that suggest that they're going to have any breakthroughs anytime soon, but I don't know the entire literature.
Yeah, I mean, that's, again, it gets back to more of a sort of a plant breeding or genetics aspect of it, rather than, you know, we've done a lot of experiments with elevated CO2, and again, it comes down to the amount of water that a plant can take up to fix carbon. So that's kind of a big thing in you know, sort of water limited systems, and it's a large part of our planet. Yeah. And we
Let me,
go ahead.
yeah,
No,
I was
no.
just going to say that, you know, there have been pretty amazing advances in what plants do.
Yeah.
Not so much in the way that they fix carbon through photosynthesis, but in the way that they allocate a huge fraction of the portion of their growth to the things that we need.
Right.
And so there have been real dramatic change, the Green Revolution, real dramatic changes in agricultural efficiency, just not through changes in photosynthesis.
Right, and it was just one last thing. So Rich's point about we've spent, you know, a lot of our resources over the years engineering plants to produce the stuff we eat and the really valuable things above ground. And now what people are saying is if we're going to fix carbon, we need to use perennial crops, right, that put more roots into the ground. Not necessarily, we don't care about protein in the grain. We want to know how much roots are in the ground. And again, it's a trade-off, right? It's either this or this. And we don't want it to be a trade-off. We want it to be this and this. And that's what we're really working towards, I think.
Well, and I think if I can
Yeah.
step out of bounds here for a second on the agricultural side, it's important to contextualize this argument about, you know, and Rich, you'd mentioned, you know, the potential risk to existing agricultural yields and things like that. This isn't either we do it or we don't. There's huge consequences to not doing it, right? So the alternative and the impact of the alternative, the floods, the droughts, the famines, et cetera, on global food productivity of not taking any remediating action. When we've had a free lunch for 140 years, it's either we take some of these more engineered and scientific and well thought out approaches, or we allow sort of the global climate change to help dominate the food cycle. And I think the former allows a better degree of equitability in terms of solution application. You don't want to commit genocide on the developing world in order to satisfy the gluttony of the, you know, existing rich, right? So I think that it's really important to remember that when we talk, like, there is going to be a hit on, you know, either economically, yield-wise. The planet just may not be able to support 10 billion people, but if we take no action, it may only be able to end up supporting 5 billion people. Right, so I think it's important context generally as we have these discussions about trying to deal with the sins of the past. There's going to be a penalty to it, one way or another.
Yeah, that's a great perspective. I'm glad that several of you mentioned corn and soybeans, because I have family in the Midwest and I drive Interstate 80 all the time. And so several questions about this industrial scale of agriculture in our country. I mean, when you drive Interstate 80, you can't help but acknowledge that, you know, half the states of Iowa, Nebraska, and Illinois are being tilled. What about no-tilling practices? What about implementing some of these things at the scale of industrial agriculture? What are the challenges you see there?
Well, Rich mentioned a couple of them in terms of there's been a sort of a rethinking of cover crops. You know, in other words, that's something. The idea of a cover crop is when you're not growing a crop for production, you're keeping the ground covered, which is a really important thing. Protects it from erosion, right? It does put carbon back into the soil. What some people are focusing on is the aspect of cover crops where that could be turned into some other product. A cover crop could be used to feed cattle or something like that. But, you know, again, I think the challenge for agriculture, and I'm speaking very broadly, is, you know, agriculture is kind of, I give talks a lot to students, and Rich and I both visit with students, and, you know, we're kind of the bad guys. You know, the ag guys are the bad guys, you know, because we're responsible for a lot of what's going on in terms of the emission of greenhouse gases from our production system. But in the same vein, agriculture has been enormously successful, right, in being able to exploit resources and do that. So we're kind of the problem, and now we're the solution, right? And so I think large-scale agriculture, there's a real interest from large companies that I've had to work with of moving toward a more regenerative mindset. I don't know if they can actually convert a lot of those systems over to fully regenerative aspects of it, but if you look at the whole system, you'd want to be more efficient with your energy use, right? Get off of fossil fuels, use solar, use wind, use agrivoltaics. If you heard about agrivoltaics, right? Putting solar panels over plants and growing crops that way. I mean, that's another aspect of it. So the scale of it's enormous, and I think that there has been a shift, but it's hard to imagine that ship's going to turn pretty quickly. You know, I mean, and I'm trying to just be realistic about it, but you know, I think that the bigger companies are interested because the consumers are interested. So you guys have a voice, right? You say something, I'm not going to buy that if this is the way you're doing it. You know, I mean, that's a really important part of this. Yeah.
What about in our backyards? A lot of people out here have their own gardens and small scale farming, and what can we do in our own backyards to try to help solve this problem at some scale?
Well, I'm not sure how big your backyard is. Mine is pretty small, but you know, some of the most intensive impacts are in urban areas. There are some changes in law that have tried to reduce those impacts, particularly things like phosphorus pollution. You know, there have been some studies. Well, lawns, if you add it up, lawns cover a pretty substantial area, and so if you can manage your lawn more efficiently, fertilize at the right time of year, fertilize 2 times instead of 4, there's some things that you can do to reduce emissions. But like you said, you know, you drive across Kansas and Nebraska, and you don't see lawns, you see corn and soybeans. Agriculture is by far the biggest user of, the most intensive use of land that's most widespread around the world, and so that's why we focus on agriculture.
Yeah, and in the urban settings, there's an interest in, you know, going to more controlled environmental agriculture, looking at green roofs. You know, that opportunity, there's a lot of research now at CSU in green roof technology. The other thing is, you know, going more toward perennial native species, right? Like, you know, we all use bluegrass, what is it? Kentucky bluegrass, right? And you know, Kentucky bluegrass doesn't fit here, right? Unless everybody's got these nice green lawns. What if your lawn was only green for like a month and then just got brown the rest of the year, right? And that's what our native grass species do, and they use less water. You know, I think water is kind of the biggest. I mean, I'm sort of going, that's kind of where my research is going. So, but I think in the urban systems, the other thing is this community food. Right? Communities, everybody growing food in their backyard, you know, I mean, having farmers markets, and those things are really important. They're creating a culture of people actually knowing where their food comes from. I hate to say that, since it can't be, but you know, we work down in Denver a lot, and so that's really a big deal. I mean, I think mostly for the next generation of people that have to solve this mess that we left them. I mean, they need to understand everything. They need to understand climate change. They need to understand energy. They need to understand where their food is coming from. And urban systems are interesting because most of the population in the planet is moving toward urban centers, right, around the world. You know, it's like 2/3 of the growth in population is going to be in an urban center. So why not develop urban agricultural systems that can be deployed to Nairobi and Cairo and places like that? I think that would be a real challenge. You know, and I think there'd be a lot of opportunity for that. Yeah.
I want to get to the other end of the table here, and a couple things on Eric and Wilson about this captured carbon dioxide. How is that stuff transported generally to the merchant market?
Yeah, no, I mean, it's a great question. Obviously, the transportation infrastructure, not just in the U.S. but everywhere, is highly carbon positive. One of the, you know, traditionally with CO2, sort of the sourcing of CO2 being localized and the demand being relatively well distributed, the majority of the tanker trucks that you see on the road today are CO2 trucks. There are very few CO2 pipelines. There's a lot in the news right now about CO2 pipelines. There's a lot of local communities that are like, highly against them. I think there's going to be a lot of resistance to getting those things laid. But unless there is, as expansive of a pipeline network in somewhere like the U.S. as there is for, petroleum and natural gas, one of the things that direct air capture can completely cut out of that equation is the transportation infrastructure. There's air everywhere. So if you can install a DAC plant at the point of use, you don't need to put a truck on the road to get it there. Many of the uses don't require liquefied CO2 either, but you need to liquefy it in order to transport it, either in a pipeline or in a truck. And so if you create that CO2 at the point of use, you save the energy of compression and liquefaction as well. There's a huge slice of sort of both the overall cost pie and overall CO2 emissions, or equivalent carbon emissions pie that's associated with the transportation of CO2 very large distances using highly carbon positive means. In the islands in the Caribbean that also have a CO2 demand, they get their CO2 from a barge that ships from Houston. And the shipping industry has some of the worst emissions globally. And so you can imagine that installing point of use CO2 generating machines it can be really, really impactful without really changing the existing market at all. So before you even start looking at disrupting things at much larger scales. I don't know if you want to add anything.
Yeah, I mean, to build on that, I mean, the co-localization of point of use CO2 is a huge advantage of DAC. You can deploy it in lots of different places in a modular sense. So if you have air everywhere, you have CO2 everywhere. Co-localizing that with power generation is also a huge benefit in that you can put solar or wind farms near these DAC centers, so you can have non-reliance on the grid or a power plant that's somewhere farther away. You can have everything a little microgrid that can have your power and your CO2 localized, and then depending on how you're using it, if you make a fuel or something that's liquid, we do have infrastructure to move liquids better than CO2 in gas pipelines. So I'd say the huge advantage of the modularity of DAC is that you can include that with the modularity of renewable energy penetration.
And I'm assuming that this localization you're talking about also helps with the leakage problem, because we know that natural gas pipelines and everything leaks, right? So what is the sense of leakage, managing leaks in the kinds of systems you're working with?
Yeah, and you're exactly right. And so if you don't have a pipeline, you can't have a leaky pipeline. So it's one of the biggest advantages. I'm no pipeline expert. Certainly there's been a lot in the news, especially recently, about the potential dangers of a pipeline that has compressed non-breathable gas that's slightly denser than air. Certainly something that is going to have to be well regulated and well maintained. But again, it's the part of the puzzle that a direct air capture solution sort of removes from the equation, one of the big benefits for it. And as Wilson has said, if that pure CO2 that you're generating from a direct air capture machine is really just an intermediate on a integrated process that converts it into a useful product, and whether it's a plastic or a fuel or a crop or something to that extent, there's really no danger, no more of a danger than any restaurant you go into that's got a bottle of CO2 plugged into its beverage dispenser.
I think one of the things we can learn from this is pulling CO2 from the air is actually how people collect CO2 at point sources currently. So that's more called carbon capture and sequestration. So, again, the biggest thing we need to do is stop emitting CO2, and then in addition, we have to pull CO2 out of the air. So if we can capture CO2 at point sources where there's high concentrations and convert it on site, there's huge advantages to reducing emissions. And the challenge there with carbon capture at a power point is that you don't get 99.9% pure CO2. You get a lot of other chemicals in there, very dilute CO2. It's not concentrated, and so dealing with those impurities, how people have done that in industrial plants now is that they don't have pipelines. They convert it, they clean it up, they scrub it, and then they convert it and either sequester it or use it for EOR, other processes on site. So I think the point that Eric made is good, is that if you don't have a pipeline, you don't have leaks in a pipeline. So using it on site, I think, is a huge benefit.
And you mentioned the market for this, which is a significant market, and the economics. Where do the positive economics come from? Is it that there's a carbon credit market out there? or that there's really an industrial need for carbon dioxide, not taking it out of formations as you talked about? Is that where the market's kind of emerging?
Yeah, it's a good question. The market is very much in flux right now. So when you look at the current industrial users of CO2, people are paying money per ton of CO2 right now, and again, it's very much dominated by where you are, geographically. If you're far away from a carbon source, whether it's a natural carbon source or an industrial carbon source, it's going to be more expensive than if you're close. If you're next to one of the few pipelines that exist, like for example in West Texas, you can get CO2 for $10 a ton. If the majority of the U.S. is 200 to 400 miles away from the nearest carbon source, many of them much further away, the average is about $300 a ton in the U.S. for industrial CO2, but it can range anywhere all the way up to $1,000 a ton in the contiguous U.S. When you look at places like Hawaii, Puerto Rico, it's $1,800 a ton. It's very much dominated by being able to get that CO2 where you need it. But there's certainly a cost associated right now for the people that buy it to use it. Now, on the sequestration side of things, obviously, if you're not making a product out of it that doesn't have intrinsic value, but rather just returning it to underground, it is very much dominated by the carbon market. Now, the carbon market is both regulatory and voluntary. Currently the voluntary market, there's about $2 billion that's committed to the voluntary market. That's expected to grow to $40 billion by 2030. In the global carbon credit market, it's currently $760 billion, and it's projected to grow to like $4 trillion by 2030. So that's more in the regulatory space. So the U.S., as part of the IRA, expanded some of the tax credits that are in 45Q, for those of you who have heard of it, that have increased for direct air capture-based CO2 up to $180 per ton for taking CO2 out of the air and sticking it underground. If it's converted to a different product, that number is a little bit less. But there's, as I said, the voluntary market, the number of different corporate entities in the Fortune 500, Fortune 2000 that you've heard of that have net zero goals by 2030, 2040, 2050. Putting aside the argument about how aggressive and realistic those goals are, it's very difficult to achieve those in any of the existing regulatory markets, and it's very much voluntary driven. So the Stripes, the Shopifys, the Frontiers of the world that have been out there in the press talking about the funds that they've put together in order to basically pay for carbon to be put back underground, either through natural means or through chemical means, really drive a lot of the early adoption into that sequestration market. But from a volume perspective, the global regulatory market is orders of magnitude higher and has 3 or 4 orders of magnitude more to go. It's estimated to be sort of a $50 trillion market by the time you get to mid-century. Again, as I mentioned before, somebody's got to be paying for trying to revert some of the emissions issues that mankind has generated in the last century.
Yeah, and I mean, I think building on that, if you want to sequester CO2, there's not a big financial market for that. It's not a product. People won't make money by putting CO2 in the ground. So a lot of startup companies in the past few years have been very inventive with what to do with CO2, and I think one of the most successful ones is a company called the Air Company based in Brooklyn. And what they did was they wanted to do a CO2 conversion using renewable electricity, and their challenge was to make a product that would make them enough money to keep them in business and let them grow. So the product the Air Company made was vodka. So they just took CO2 and they made hydrogen with electrochemistry, so green hydrogen, used Con Edison electricity from New York City, and they made very pure ethanol. And they're able to sell vodka. It's pretty decent if you ever get out to New York or Brooklyn. It's very pure. They can sell it for $60 a bottle because people in New York City will buy it. So from that, they were able to grow their business significantly. They now have 3 different plants. A 4th one is going to open soon. When the pandemic started, they used the ethanol that they made, in addition to making vodka, to make hand sanitizers. Then they learned how to make perfume, and they recently just signed a tens of $1 million contract with the U.S. government to make sustainable aviation fuels. So that is one of the markets of if we can make jet fuel out of air instead of from fossil fuels, and the company can't start with that because you can't compete with the big travel companies if you're a small company. So they got their foot in the door with a high margin product, making vodka. People bought enough of it that they could grow, and now they make several products, and they are going to be, they've actually made the first fuel that was ever used to fly an airplane, so made from air and renewable electricity. So that's a company they're growing, and there's a lot of other companies that are trying to get in there. The sustainable aviation fuel Huge market. Planes and shipping are responsible for a lot of emissions. So you don't remove the emissions from burning the jet fuel, but if you can get the jet fuel there from air instead of a fossil fuel, there's significant less CO2 emissions. So vodka and jet fuel seem like good markets for CO2 at the moment.
So maybe we're going to go from craft beer to vodka here in Colorado.
I'm game.
You mentioned underground storage, and you know, back in the day, it seemed like the main way in which we were talking about storing carbon was underground reservoirs, geologic formations. A couple questions about, is that still a big piece of the carbon capture approach, and what about leaks, and you know, can we afford to find these big formations and hold those for carbon capture? What are your thoughts on that?
Yeah, I'll start, and then, but recognizing I'm no geologist, so yes, it's a huge part of it, right? So the sequestration market, the volumes there are going to be 6 orders of magnitude higher than any of the, even if we transition to a renewable carbon-based economy away from fossil, it's still going to be significantly outpaced by sequestration. That is very much focused on stable geologic formations that can hold it. The EPA's got a permitting process for those types of wells. It's called a Class 6 well permit. There are very few that have currently been issued, but there are a number of applications in. But it's like a 2 to 5 year process to get it done. There are other means of storing those things underground. You know, some of which is injection into basaltic formations that form these more stable carbonates that Wilson was referring to earlier. You can also do it not subterranean, and I think that's a lot of what you know, the gentlemen on my right have been speaking to a bit, and that Wilson was commenting on in terms of enhanced weathering type applications as well. But there's a huge question about both permanence. So how do you audit and maintain the permanence of CO2 that's been injected underground? Not just so that you're not injecting it underground, collecting a check, and then collecting it again and re-injecting it, but also from a safety perspective, right? It needs to be, that's basically the entire point of the permitting process is to allow, you know, all of the you know, expert geologists to assess the subterranean rock formations and to you know, be able to validate their permanence. And there's a lot of monitoring that goes on, an extensive amount of monitoring that others at the table may be a little bit more familiar with.
So we mentioned soils, underground reservoirs. What about the oceans?
The oceans are very complicated, and people are looking now to use the oceans as a reservoir for CO2 capture. So essentially, you know, what Eric and the DAC company wants to do is build these big fans, like he said, and you take the CO2 out of the air at 400 ppm. So it takes, you know, time, space to build these machines to do it. The ocean itself, which covers 2/3 of the surface of the Earth, is spontaneously capturing about 30% of all CO2 emissions on the planet. So in terms of doing the front end of capturing the CO2, the ocean is a huge reservoir. Now, the complications with that are the ocean absorbs more CO2, it becomes more acidic, and that is making life very hard for things to live, which will have effects on humans as well. And so the challenge is the approaches want to make the ocean less acidic. So they want to do, you know, enhanced weathering and alkalinization, but we have no idea what effect that's going to have on plants and animals. And so the idea sounds nice, but especially shoreline communities in plants and animals, if you just dump a bunch of alkaline solution in there, it's going to have effects on the ecosystem. And so the option is there, but I think we have no way to monitor or verify plant and animal life if we were to do ocean engineering.
Yeah, well, there was quite a bit of research 15, 20 years ago on ocean fertilization, you know, so especially in the southern oceans, fertilizing with phosphorus, or not phosphorus, iron mostly, and silica, actually. Silica is a limiting element for phytoplankton and stuff. So, yeah, I mean, I think you run into the problem of acidification, and I think that's kind of becoming, the ramifications for that are huge. So,
I forget who said it, but somebody said, if you give me a tanker full of iron, I'll give you another ice age, implying that it was really iron availability that limits photosynthesis in the ocean. And of course, the experiments that Gene talks about, they did, you know, fertilize the ocean, and yeah, there's more algal growth, but then unfortunately it all decomposes, and so you don't get much carbon storage that way. The only thing I would add is that you know, from the perspective of managing ecosystems to sequester carbon, we don't manage very much of the ocean. It's really difficult. So there's lots of enthusiasm about doing a better job of managing coastal kelp forests, for example. There's a company called Running Tide that has this idea that they can grow you know, seaweed on these buoys and then send the seaweed out to the middle of the ocean and then sink it. yeah, that probably would sequester carbon, but it's hard to imagine how we get some of those things to scale.
Right, and then the idea Rich was talking about, I mean, these coastal areas are considered to be the, you know, highest net primary production on the planet, right? At the interface of our continents and the ocean, but again, it's northern hemisphere, right? And not a lot of coastal area actually for that, so.
I mean, if you drive up and down I-25, which I'm sure all of you do, one thing that's not going away is concrete.
Yeah.
What about injecting CO2 into concrete? There was just an experiment done on this up in Wyoming that had apparently some measure of success. Any thoughts on that?
Yeah, I mean, there are a number of companies that are looking at using concrete as a permanent storage for CO2. I mean, concrete, the cement industry, besides the transportation industry, is the largest emitter globally, right? When you have these large cement factories, they generate the powder that turns into cement when you add water by basically driving CO2 off of running these calciners at very high temperature, very energy intensive, releases a lot of CO2 when you generate it, and it's I think it's something of the 30% of the non-transportation industrial emissions are from the cement industry. So there's a huge driver, not just for trying to reduce the amount of CO2 that cement manufacturing releases by recapturing it or using cleaner energy to drive it, but also recognizing that when you turn that back into concrete, cement doesn't dry, right? There's a chemical curing, and that is through, to some extent, hydrate formation and the other carbonate formation. And so you can add more CO2 to a cement mixture and sort of push it more towards the carbonate formation. There's some argument that it creates, stronger cement, but certainly can recapture some CO2 in doing that. So there's, I think one of the first companies to do it in Carbon Cure that's based in New York. There's others like Solidia and some of the Carbocrete folks, and as you were mentioning, the UCLA-based technology that was demonstrated in Wyoming earlier. It's concrete. Mankind's appetite for building infrastructure is enormous, and as sort of the developing world becomes more developed, it's going to continue to expand. And being able to not just reduce the net emissions of building new infrastructure, but potentially use it as a long-term carbon storage tool is really valuable.
We've got about 15 minutes left. I want to give each of our panelists a time just to summarize their own thoughts from what they've heard, the discussions, and they can, I think a lot of the audience would like to hear your personal opinions about pessimism versus optimism on some of the scales of these things that we're talking about. Things about, can we really get an honest assessment about what it's going to take to convert all this CO2 that's still being produced? What kind of government policies do we really need to be seeing in order to really make some of these things stick? And where's the funding going to come from all this, both at the research level and at the industrial company level? So I'll give each of you a couple minutes to kind of summarize your thoughts and kind of pick and choose from those ideas. Rich, do you want to get started?
Well, I guess I'm an optimist. Maybe a naive optimist, maybe a sunny optimist, maybe a rational pessimist. I don't know, but there are a lot of things to be encouraged about. Like I mentioned before, this Inflation Reduction Act is enormous in many ways, and it's going to change the direction of our lives right now. There are lots of reasons to be optimistic about the future of some of the emissions from some of the big sectors. The emission reductions in the energy generation sector have been unbelievable. As I said, I've been teaching this course. I teach since 2013, and I love teaching it, but boy, it's a lot of work. Sometimes I wish I taught chemistry instead, because I could just teach the same thing every year. But as it is, I've got to change all my lectures every year. It's more work than I signed up for. But that's good, right? Because that means that we're making progress. And so talking about the energy sector, when I started, I was talking about the Clean Power Plan, which had big ambitions to reduce emissions from electricity generation. And it turns out that by the emission goals in the Clean Power Plan, which has been overturned by the Supreme Court, we met those goals in 2019, 11 years ahead of the ambition. And the reason is because the learning rates in renewables have been so steep. So as we continue to deploy more wind and solar, the price just drops through the floor. In the last 10 years, the price of wind has dropped by more than half, and the price of solar has dropped by 76%. I mean, it's dramatic. And as we deploy more and more, it's going to continue. It's amazing. It's Moore's Law for the renewables. And another reason to be optimistic is that it's not just those sectors. There are lots of sectors that function that way. And so if we can identify technologies that help us reduce emissions that have these enhanced learning rates, then the clever people in our Congress have figured out how to incentivize those through policy. And I think that those are the policies that make sense. Let's drive the price down of alternatives and encourage technology to take over where it makes sense. It's not about picking winners. It's about picking technologies that in which we can improve efficiency. Everybody's a winner. And I hope that those learning rates apply to lots of other fields too. I imagine that if the crazy stuff that we're doing in the lab is successful, that just by doing, we'll be learning. I'm optimistic too because there are, there's widespread recognition that this problem is real and it's something that we have to tackle. And it comes with a lot of co-benefits. If you think about the benefits of that we're realizing through the deployment of renewable energy, the health benefits alone from reduced air pollution are, tremendous. It's amazing. So lots of synergies between things that will reduce emissions and other benefits as well. And finally, I'm optimistic because there's so much interest in this now. Every day I read about a new company, a new idea, a new policy, a new startup in this arena. And so lots of people are really thinking about this. And the more people we have working on this problem, the more likely we are to come up with creative solutions that we can implement at scale. So, some days I'm pessimistic. You caught me on a good day. I'm feeling pretty optimistic.
Gene?
Thanks, Bill. I was telling somebody this morning, when I give a lot of these, or I go on a lot of these panels now, and I look at the audience, and whenever I see a lot of legislative assistants out there, I go really dark, right? I sort of want to push people, and I'm not very optimistic. And then next week, I have to talk to 600 high school students, right? The person said to me, can you just try to be optimistic? And so I'm really working on that. So this is a good practice for me. I agree with everything Rich said about the energy sector and the idea that innovation is really something that we're going to have to really move on in terms of investments in innovation, I think are really critical. From the perspective in my platform in agriculture and food production, obviously it's really easy to say, big ag, ag is broken, and it is. And so my view is that we really need to look at a comprehensive sort of a rethinking of the way we produce food globally and the way food is distributed globally. I find it appalling that the little bit of investment that goes into our agricultural systems, particularly in the U.S. and a highly industrialized nation. Our mantra with regenerative ag is that we need to use regenerative processes, and regenerative is not going back to anything, it's going forward. The systems that we're talking about are not the systems we used prior to the 1900s, it's systems that don't exist. And so regeneration is really about innovation and technology and thinking of ways to produce food to sustain the planet in a socially equitable way that does no damage. And so I'm optimistic from that standpoint. I do think that what has to happen is we need to rethink agriculture and our soils, and that this is infrastructure. Food is infrastructure. It's like roads, it's like pipelines, it's got to be treated that way, and it shouldn't be treated any other way. So enormous investments. I think my colleague Scott Denning always says, this whole fossil fuel thing is crazy. We could electrify the world with 1% of the GDP. And there's got to be something like that with agriculture and food production. So anyway, I'm optimistic for a number of reasons. I think the next generation of people that are coming through CSU and at CU, and I think there is a consciousness that's sort of bubbling up. And I'm optimistic about that. And I tell students frequently that I'm in the last 10K of the marathon of life. And so I'm going to sort of work and be a bit more of an activist. And so anyway, that's what I hope to do. But I am optimistic, and I think, with the progress we've made in terms of technology and innovation, I mean, you guys are all sitting on your iPhones, and think of all the knowledge you have at your fingertips, right? And we just need to be careful with the way we're using it and making sure that it's again, a just way of sharing information and technology globally. So anyway, I think I'll close there.
Thank you, Gene.
Yeah.
Yeah, great. So, I mean, I think you've heard it that for climate relevance, it really requires scale. And, you know, the IPCC, the national academies, everybody, it's fully accepted now that reducing emissions is not enough, right? We've got more than a century's worth of emissions that needs to be recaptured and restored, and we've got less than 10 years basically to do it. So, you know, as Rich mentioned, it's going to take a portfolio approach to meet those sorts of scales. There's no winners, there's only contributors. You know, Global Thermostat's got a DAC plant that's operating. It's on your way to the airport from here. It's about half the size of this room, and it does the work of like 30 to 50,000 trees in terms of the amount of CO2 that it can remove from the air. So from a density perspective, it's great, but again, it doesn't take the place of protecting the forests, avoiding deforestation, working on active afforestation. But it's something that can be applied in anything from an urban environment to a rural environment, depending on what it's being used for. There's, you know, the need, the scale of the problem, you know, that plant can do, you know, 30 to 50,000 trees a year. The scale of the problem is 10 million times bigger, right? So it's a drop in the bucket. You know, the need to convert the fossil-based economy into a renewable carbon economy, the need to, you know, completely change our energy use portfolio from being fossil-based to renewable, the need to recapture historic emissions. These are all sort of different slices of the overall carbon profile pie that are attacked by, you know, a number of different types of technologies. Direct air capture is a necessity. It's part of that arsenal, and, you know, the scale to which it can be deployed, we will get as much out there as possible to try to remove as much CO2 from the atmosphere, and whether it's converted into useful products or directly stuck back underground. Either way, it's a replacement for, you know, the exact opposite, which is going on today, pulling it out from underground to directly use it and re-emit it. It's something that, you know, because the scale of the problem is so large, it's easy to be pessimistic, as you've heard, you know, about how we're going to deal with this. And I think you know, we're seeing a lot of it. You know, in 7 days' time, we saw setting a new cold temperature record and setting a new high temperature record, you know, in the space of 7 days in the last week, right? So those types of extremes, you know, the long mega droughts, the huge floods, the fires, the storms, the tornadoes, it's all going to lead to sort of the recognition that if we don't do anything, the penalty's bigger than if we do something. And, you know, I think all of us are going to bear the costs of that. And the goal, I think, of this entire panel and the industry writ large is to minimize the overall impact of kind of those sacrifices, so to speak, be they economic or lifestyle or otherwise, to try to allow us to get to sort of mid-century and beyond without, you know, having to deal with a massive depopulation event. So.
Well, I hate to end on a other note. I actually am not optimistic at all. I'm very pessimistic. I mean, I'm just being honest.
You're having a bad day.
I mean, just every day, and it comes from. I mean, I agree with everything everybody said. We need to do this. We have to do it for the longevity of our species on the planet. We need to do it. But I'm pessimistic because I've seen how, you know, learning how we got to where we are today and what we would need to do to make this future. I just don't have faith in the global population. That's just my opinion, and primarily because something we didn't talk about today, but is implied with almost every scenario looking forward, is deep decarbonization, which means electrification of everything. And it was brought up, we have the ability to electrify. If we were to electrify everything, which is every scenario looking forward, you know, 1.5C, that's a joke, we're already past that. You know, 2C probably won't even hit that. That's just reality. In order to get to any scenario that looks beneficial and not catastrophic in the future, the amount of precious metals that we're going to need to extract out of the earth is going to be more than 10 times everything we've mined up until this point collectively as a planet. We're going to need to mine at least 10 times that moving forward. And where these precious metals are located, the sovereignty of the people whose land gets taken from it and they don't get to get the riches from the excess, the amount that we're going to need and how that was done to this point. If I was optimistic to say we'd get there, and if it was done the same way, that's terrible for humanity, maybe better for the atmosphere. So I'm pessimistic because of how we got here, and I don't think that there's enough incentives, and it comes down to, I think, finances for people to make right decisions for the benefit of humanity. It's making a dollar, capitalism, especially in this country. So sorry to get on a horse, but that's just my feeling. But that's what drives me to work on it, my pessimism, thinking it can't work. So we need to innovate. We need to do better, faster, bigger. So I use that as a motivation to work harder, not to not to give up, but I am pessimistic. Sorry to end on that note, that's terrible.
That's fine. I know a couple years ago, we had speakers here from the TV series Mars. And if you watched any of that, you know, it was basically the humans going to Mars and starting to live there. And we started extracting everything, right? We went right back to the same practices we've done here on Earth, you know, which does not seem to be a good solution.
You know, it may be positive there. So the Air company who makes vodka, they have several projects with NASA, and they are actually going to be 98% of the Martian atmosphere is CO2. So they're going to be mining the air on Mars as a resource of carbon using the same technology. So there is promise.
Okay.
Just not here.
Yeah, it's not here.
Well, thank you to the audience for your attendance and for your piercing questions. And for the, let's have a round of applause for the panel here. Thank you. And I don't know, this will be the formal end. I don't know, I don't think there's anything in here immediately, so I'm guessing one or two of them can stick around if you have a few questions and you want to come up. And again, thank you. Thanks, guys.
Oh, that was fun.
It was fun, yeah.
Continuing education knows that at the end, students want to graduate, and we can help them do that because we take the time to really listen to their needs, and we understand all the different options that are available across the campus for them.
We don't take a cookie cutter approach. We realize each student comes with their own story. So whether it's a part-time student looking to complete a degree program or someone just looking for online courses, we're there to connect them to the resources of the university.